Okay, we're going to be working with rational expressions in this video that have radicals in the denominator. Okay, so what it says here, we're going to simplify rational expressions by rationalizing the denominator. Okay, this is a process of simplifying a fraction type looking expression, but it has radicals in the denominator. So let's take a look at some examples of what these problems will look like. And if you notice here, they just kind of look like fractions, but they have radicals in the denominator. It could be a radical in the numerator, but having the radical in the denominator is where we consider it to be a problem. The thing you need to learn here is that when we have a radical in the denominator, the expression is not simplified. Okay, that's just a little bit of a funky rule in math you encounter. And this video is going to talk about learning to simplify these expressions by kind of getting rid of the radical on the bottom. Okay? Some other examples of problems you'll see in this video kind of look like this, where again they're fraction-looking expressions, makes them rational, and there are radicals in the denominator. Again, the radicals are the square roots. So for this reason that there's a root 5 in the denominator, this expression's not simplified, and similarly here, it's not simplified. So how do we deal with these expressions? That's what we're going to specifically do in this video. We're going to talk about taking expressions like this and going from not simplified to simplified. Okay? So before we get going, old rule that you should know by now just comes up a lot in this video is root a times root a is equal to root a squared, and that in fact simplifies to a. So basically when we have a root times itself, you just get the radicand, which is the expression under the radical sign. Okay, so something as simple as root 3 times root 3 is equal to root 9, which is 3. Okay, so simplifying expressions with monomial radicals in the denominator. Okay, I'll do this decently mechanically, okay, with some steps. Step 0 means you should look for it, but you might not have to do it. And it says simplify any radicals in the expression. Step 1 is to multiply by 1 in the form of the radical in the denominator over itself. Step 2 is to simplify. Now the real magic happens when we do the step 1 that's in green. And I'm going to try and color code my steps with how I'm moving forward here working in this video. It's really where the magic is, like I said, multiply by 1 in the form of the radical over itself. Well, it should make sense to say when we multiply by 1, we're not changing the expression. And that's the most important thing you realize when you do this. You're not changing the number that you have in terms of its value. You're just changing how it looks. So move right into the examples. These problems go very quickly once you start learning the little tricks here and how to do them. So how do we simplify the opposite of 2 over root 7? Well, the first thing I'm going to do is simplify any radicals in the expression. And root 7 does not get simplified to anything but root 7. So now here's the deal. I notice the radical in the denominator is root 7. I need to know that for step 1 here. Multiply by 1 in the form of the radical in the denominator over itself. Well, that just means I'm going to multiply by root 7 over root 7, because that, in fact, is the number 1, which means I'm not changing the given value. But when I multiply across, like I do with my fraction rules, something really cool happens. I get the opposite of 2 root 7 over root 7 times root 7 is just 7. So we see that we've had a radical in the denominator in the original expression right here, and in the final expression we don't. That's why this is considered to be simplified now. A little bit of a weird word, but you've rationalized the denominator. Okay? Step 2 in red says just to simplify. Well, I'll just circle this in red because there's nothing to simplify there. Remember, with the in within rule and the out without rule, you cannot cancel root 7 over 7. They're not kind of like terms a little bit. Not totally the right expression for that, but it will suffice. So in number 2, where I have 7 over 4 root 8, the first thing I do is step 0, and it says simplify any radicals in the expression. Well, I'll do that here in the margin a little bit. Root 8 can be simplified. It is, in fact, 4 times 2, so that becomes 2 root 2. So I can rewrite the expression as 7 over 4 times 2 root 2, which is 8 root 2. Step 1 says multiply by 1 in the form of the radical in the denominator over itself. We'll take a note here that this problem is a little different than the original. This says 8 root 2. Well, I don't need to multiply by 8 root 2 because it just says very specifically in the directions, just multiply by the radical over itself. So in green, I will do that. It will be root 2 over root 2. Again, that's just 1, so I'm not changing the value. And then when I multiply across, I in fact will get 7 root 2 over 8 times 2, because root 2 over root 2 times root 2 is just 2. So what does this give me when I go to simplify? It gives me 7 root 2 over 16. This fraction cannot be simplified. Here are the 7/16, so in fact, that is the final answer. So here, example 3. If you notice here, it says step 0, simplify any radicals. Now, I could actually simplify here using the in with in rule and the out with out rule. Okay, I'm just going to kind of just hold off on that though. You could. These rules are these steps are more guidelines than hard and fast. There's a little flexibility here, but this will help you start to address these problems. And you'll see some shortcuts maybe as you go. So here I'm just going to go right to step 1 because I really can't simplify the root 5 or the root 10. And that is going to give me an opportunity to multiply by root 10 over root 10. Again, just using just the radical in the denominator. And this fraction is just 1. This gives me, while multiplying across, root 50 over 4 times 10. Okay? So from there, I'll need to simplify. So at first, I'll put root 50 over 40. But I also need to realize my root 50 can be simplified, which is going to give me 50 broken into 25 times 2. Square rooting that is going to give me 5 root 2. Okay, so I replace that. I get 5 root 2 over 40. Now I can actually, when I see this fraction, I actually can simplify the 5/40ths by dividing both by 5. That gives me root 2 over 8. Okay? Another good way to check your final answer is to take this number on your calculator that you started with and take this number on your calculator that you finish with and see if they are in fact the same thing. Okay, so just quick review of this. When dealing with a monomial radical in the denominator, the key rule here is to multiply by 1 in the form of the radical over itself. Again, just the radical that's in the denominator. Okay, so let's move on to problems that are a little bit harder here. And we see here that in these problems, we're given rational expressions that have a binomial in the denominator with a radical, okay? And we see here, this is going to be a slide where I show you how to simplify expressions with binomial radicals in the denominator. So before I do that, there's a little side step we got to make. You have to understand something that's called the conjugate, okay? And a quick definition here, the conjugate in and of itself, what it is very simple. How to use it is a little more complex. So if we have the conjugate of a plus b, we say that it is a minus b. And if you have the conjugate of a minus b, we say that it is a plus b. So if you notice, it's just, if you're given a binomial, the only thing you do is change the sign. Change the operation is a more formal way of saying that, from add to subtract or subtract to add. So just real quickly here, it says state the conjugate of the following. So we have 5 plus root 7. The conjugate of that is 5 minus root 7. Again, the only thing changing is the operation. And if we have 15 minus root 8, its conjugate is 15 plus root 8, keeping in mind that you could simplify the root 8. Okay? And then this next expression where it says negative 2 minus root 11, it's negative root 2 minus root 11. It's negative root 2 plus root 11. Now again, the one thing you need to focus on here is this was a negative, it's still negative. The only thing I changed was the subtraction to an addition. Okay? So how do we use this? Well, you'll see how it works when I start doing it. It's kind of a cool trick. Okay? So let's look at our steps. It says step 0, simplify any radicals, I should say any radicals in the problem. Okay? And step 1 is to multiply by 1 in the form of the conjugate of the denominator over itself. Okay? Easier done than said. It's a mouthful, but when I do it, you'll see it quickly. Then 2 is simplify. Okay, so we notice here in this expression, if we're asked to simplify, we realize we have to, again, because there's a radical in the denominator, and this is unsimplified just by definition. So what do we do with this? Well, we're going to multiply by 1 again, but a very particular one here. And it's what we say here in step 1. Multiply by 1 in the form of the conjugate over itself. Well, the conjugate of 2 plus root 3 is 2 minus root 3. So when I do that, you see me writing in these parentheses for the multiplication because it's going to create a distribution on top and a FOIL problem on bottom. Okay? So I'm going to do that multiplication now, and I'm going to get 5 times 2 is 10, and 5 times negative root 3 is 5 root 3. Having the radical on top in the numerator, totally fine. So now I'm going to do the FOIL problem for the denominator, and it's going to get 2 times 2 is 4, and then 2 times negative root 3 is negative 2 root 3, followed by root 3 times 2 is positive 2 root 3, followed by root 3 times negative root 3 is just going to give me minus 3. Okay? Now if you see here, this is what's cool. I've used the difference of squares model, so to speak, to create a situation where the middle two terms cancel, and that's where the radical is. So I'll continue to simplify here and get 10 minus 5 root 3 over 4 minus 3, which is 1. So that just gives me 10 minus 5 root 3. And obviously, because this is no longer even an expression that looks like a fraction, I definitely don't have a radical in the denominator. It doesn't always happen that you cancel the entire denominator. It just happened to in this example. Okay? So now I'll move on to a little trickier example. If you notice here, this is a rational expression that's a binomial in the numerator as well as the denominator. So this will be a little more complex, but it should be, easily followed as well in this example. So step 0 is simplify any radicals in the problem. Well, I can't simplify root 2 or root 5. So now I'm going to multiply by 1 in the form of the conjugate of the denominator over itself. So here we go. What's the conjugate of the denominator? I believe it's 7 plus 2 root 5. And again, respecting the fact that you have to multiply by 1 means I'm going to multiply by the conjugate over itself. Because again, multiplying by 1 does not change the value of the given expression. Okay, so a little more complex here because it's a FOIL problem on top and bottom. So let's see if I can just follow that out. And a set of parentheses for this numerator is going to help illustrate that more accurately. Okay, so what do we have? We've got 5 times 7 is 35, and then 5 times 2 root 5 is 10 root 5. Okay, followed by root 2 times 7, which the root 2 is negative, so it's negative 7 root 2, okay? Followed by negative root 2 times 2 root 5 is negative 2 root 10. Again, using the in within and the out without rule. The 2 gets multiplied by the 5 because they're both radicands. Now, that is all over. Foiling the bottom, 7 times 7 is 49, followed by 7 times 2 root 5, which is 14 root 5, followed by negative 2 times 7 root 5 is negative 14 root 5, followed by negative 2 root 5 times 2 root 5 is actually going to be, and I'll just go in the margin for that so you see it, it's going to be 4 times root 25, so it's 4 times 5. Again, it's negative because the signs are different, and that is going to be minus 20. Again, quite nicely, you're going to cancel these radicals and do further simplification and just get what? 35 plus 10 root 5 minus 7 root 2 minus 2 root 10 over 49 minus 20, which is 29. So, we see here our end goal is met where we do not have any radicals in the denominator, and this in fact is now considered to be simplified. The irony here is this looks a little more complex than the thing I started with, but we talk about having radicals in the denominator as a problem in math, so we consider it to be not simplified. So you need this skill. So I hope this enlightened you. Just a quick review. We looked at problems where we rationalized a monomial, radical out of the denominator, by just multiplying by the radical over itself. And here we then, looked at opportunities to rationalize a radical out of a binomial in the denominator by multiplying by the conjugate of the denominator over itself. But the one thing I hope you see, and this is a great theme in math, is multiplying by 1, multiplying by 1, multiplying by 1, and multiplying by 1. So none of these values from the given changed. Enjoy. I hope this was insightful. Do some practicing, and feel free to rewatch if you need to.